Thank you very much. Yeah, so thank you very much. And I would like to thank organizers for asking me to give a talk. And actually, I was a bit confused because my expertise is definitely not enough to help non-commutative geometry and topological recursion to meet. But then I decided that what I can do, I can start with topological recursion and show in which what kind of commutativity is hidden there, and then try to get out of this commutativity. And if you want, so my talk can be considered as a sort of grand proposal of what can be done of sort of non-commutative flavor, but that has nothing to do with the non-commutative geometry from the previous lecture, but has a lot to do with various kind of algebraic and enumerative geometry. So what can be done as a sort of extension of topological recursion theory? So this is along the lines of my, well, it's, so we are writing with three of us a paper. So this is with Volodya Dotsenko and Pedro Tamaroff. And that's basically what I'm going to talk about is something purely algebraic. And so it's just really the story about algebraic structures. But so what I think about it is that it's a quite interesting story. So I want to try to explain what I'm doing. Good. So yeah, first thing, maybe also what I had to do is to put both Arnold's trinity and algebraic 2D gravitation theories in quote marks. But so let's assume I did this. And then I want to start with topological recursion without actually explaining what it is. So for that, we have lectures of Elba. And so just I want to say that topological recursion, somehow what it always produces, this or that way, it always produces the so-called cohomological field theories. And so I don't have to explain what it is, so it's not needed for this cohomological field theories. It's not needed for my lecture. I just want to sketch so just a few structures that are related to topological recursion. So maybe I have to put here that mainly I'm thinking about semi-simple, but it doesn't matter, as I said, for my lecture. So at the moment. And so what is a cohomological field theory? I need just a small bit of its structure. Namely, I only want to consider something at the tree level. So tree level. And at that moment, so people start to think about, well, what people call Dubrovin-Frobenius manifold. But even a Frobenius manifold structure is too much for me. So I want to get even less. So I want to have, well, in principle, when people start to ignore scalar product, so no scalar product. And then people start to talk about flat F manifolds. But I want to have even less. I also want to have no unit. So, and that's actually, so I'm coming to the structure that I'm going to define, because so far it's just names which are not really important. So no unit. And then what we get is typically called in the literature hypercommutative algebra. Okay, so now we see that indeed we have something intrinsically commutative inside topological recursion, right? So I started with topological recursion, did something that what Elba is explaining we have to do, but well, then if I go down, I mean, forgetting a lot of structure, then I get to something that is called hypercommutative algebra. I'll give a precise definition. I'll give a precise definition.
Sergey?
Yeah.
Shouldn't your inclusions be in the opposite direction?
It depends on what you apply inclusions to. I apply inclusions to the number of structures and words you need to define particular structure. So, but if you talk about examples, then the inclusion is of course in a different direction. You're right. But that's a kind of important to say that I am not going to focus on any examples at all. It's really only important for me to talk about algebraic structures. So in this sense, the inclusions are correct. But thanks for your remark. Yeah. Good. So now I am ready to explain. I'm ready to explain what is okay. This what I call 2D algebraic 2D gravitation theories. So that's let me try to. So this one. Okay. So algebraic 2D gravitation theories. I'm not sure that it's a good term, so I need some term for the following. The point is the following: that hypercommutative algebras, they don't come by themselves. There is at least 4 different types of algebras. So when I'm saying hypercommutative algebra, I'll define it in a second. But you can think about associative algebra, Lie algebra, and then okay, hypercommutative algebra. So that's also a type of algebraic structure. But there are more algebraic structures connected to each other, and they're connected via various dualities, quotients, homotopy quotients, and so on. And they all together, these algebraic structures, form what I want to call algebraic 2D gravitation theory. So basically, let me again give first names. So the names would be like hypercommutative, hypercom. So then also something that is called BV algebra. So something that is called Gerstenhaber algebra, and something that is called gravity algebra. And the point is the following: these 4 algebraic structures are closely related to each other in various ways. And the point is the following: so when I'm using this term algebraic 2D gravitation theory, I really want to say that I have 4 interacting algebraic structures. And today I will just focus on 2, on these 2. And I want to discuss some results related to them. And so then how and why we should try to get out of commutativity of hypercommutative algebra. Okay, so now I'm ready to give, well, mathematical part of the talk starts, but the philosophical part also, I mean, it's not finished, it's come later, it will come later when I'll explain what Arnold's trinities are. Okay, so what is a hypercommutative algebra? So hypercommutative algebra is the following. So basically you have to say that you have an algebraic structure on some vector space where you have operations. So usual commutative algebra, you have just one operation of arity 2, which is commutative and associative, right? So hypercommutative algebra is the following. We have operations of each arity starting from 2, of arity 2, of arity 3, arity 4, and so on. So when I draw like that, I mean that it all kind of operations acting on some vector space, and you have to put at the leaves of these trees the inputs, and then read at the root the output. So I mean that this is, for instance, for me, is a map on some vector space from V tensor 4 to V. So this is 4, right? So I just mean that we have this kind of independent operations, and each of them is totally symmetric in its inputs. So that's basically this hypercommutativity. And yeah, so maybe also I always want to think about homologically graded vector spaces. So when I'm saying vector space, I used to add in mind differential graded vector space, and I mean homologically graded. And so then I want to add homological degrees. And for this, it would be 0. For this one is 2. For this one is 4, and so on. And then these guys should satisfy some relation. I mean, in the normal commutative algebra, I would say that I only have the first one, and that it satisfies the relation that is associativity. And the point is that the relation that I want to have for all of these guys is also associativity, but associativity in the sense of what people got in Frobenius manifold. So associativity equation, this Witten-Dijkgraaf-Verlinde equation. So basically what I want to have is the following. So relation is the following. So if I take any
Sorry,
A1,
the image is not sharp.
sorry?
The image is not sharp, the image of the blackboard. It's blurred.
Ah, I'm sorry.
I don't know whether somebody else could confirm this.
Maybe you can put the blackboard on the top a bit lower.
Is it better?
No.
There's a problem with the camera. Maybe there's a dust on it, or
It's just not focused. The camera is not focused.
Exactly. Mhm.
uh-huh.
Oh, now it's better. Yes.
Good.
Now it's fine.
Okay, yeah, sorry.
Okay,
Yeah,
thank
sorry.
you. Thank you.
Okay, good. So what I basically want is the following. So if I take any vectors in my vector space, and so then I can do the following. I can split them in all possible ways into groups. So I say that I have split them in all possible ways into groups, so that this is equal to 1n. And then I apply one operation of the corresponding arity to AI. So this I mean just that I take all the guys with the indices in I, and then I take all the apply also the operation of the corresponding arity to the output of the first operation, and here I substitute also all vectors with the indices in J. So I consider this kind of thing, and so then I'm requiring that for any indices I, J, K, such that, okay, so I and J are in I, and K is in J, that this sum would be equal to exactly the same sum, exactly the same, of exactly the same picture. So now I see that giving online talks is a bit better because I could just cut and paste here. So AI, and here is AJ. And again, so I disjoint universe J is again N. And then I want IK to be in I and J in J. So this is what is called the associativity equation. Well, maybe this is the oriented, how people call it, version of associativity equation. And if you try to apply this, assuming that all operations except for the first one are equal to 0, you would just get a usual commutative associative algebra. But this structure is much nicer. It's quite important. It's what the whole quantum cohomology or genus zero Gromov field theory is about, is how to produce these operations from natural geometric sources. And so the point is the following, that this is something that is always sitting in the background of topological recursion. Good. So now I want to show you a sort of example of relation that we have between the structures that I discussed form for me this algebraic two-dimensional gravitation theory. Namely, I want to define what is a BV algebra and show what kind of relation we can have here. So what is a BV algebra? But BV algebra is a bit so something that is already well understood. So I want to define a sort of BV algebra, if you don't mind, BV. So what is BV algebra? BV algebra in general is the following. Yes. So it's commutative. Oh, maybe first I'll define just BV algebra. It's commutative. Again, commutative. You see, we all try to get something non-commutative, but it's still commutative. Associative. Associative, well, differential gradient, I always omit algebra. Equipped with an extra operator. So delta. Okay, algebra, let me say it's A, for instance, with delta that acts on A. Such that delta squares to 0. And delta is of second order. With respect to the product. Okay, so that's what a BV algebra is. Thank you. Good. So the point is the following. So I'm going to explain you a way BV algebras are fundamentally related to hypercommutative algebras. But the point is the following. So one thing that I want to add, and that's a new thing that we got in this paper with Dotsenko and Tamaroff is you see. So the point is that this is something that I would now call 2BV algebra. And I would say, because you see, so why it's from algebraic point of view, there is no point to consider exactly operators of order less or equal to 2, right? We can also consider the operators of order less or equal to any B, right? And then, so this is something that I would call BV algebra, if it's like that. So the operators of order 2 are of fundamental importance because of their role in various interpretations of topological string theory. But yeah, I don't know. I mean, it's kind of so for this kind of question. I mean, so why? What algebraically would change if you change 2 to B? I don't know. It's around, for me, it's around about 20 years, because I was working a lot about 20 years ago on this kind of topics with Andrei Losев, and he kind of predicted that there should be a beautiful answer to that as well. And so I want to explain a bit more about that. So first, I'll explain you the classical result. The classical result that is sort of somehow essentially. I don't know if you know some of categorical Gromov-Witten theory, or where are my notes, or BCOV theory, then this kind of result comes back many times in the constructions of the theories. Namely, so what I want to say is that, well, categorically, if you speak about BV algebras with homotopically resolved delta, I'm going to explain what it is just the same as to speak about hypercommutative algebras. That somehow from well, categories are just the same categories. So you have explicit quasi-isomorphisms on the level of algebraic structures. So let me explain what I mean by that. I mean by that the following. So imagine that you have, okay, so now I'm saying, so BV algebra, I maybe add B later on. And so then I want to say the following, that BV algebra A, and I want to say that, okay, so I have the differential. I always said that my vector spaces are differential graded, so I have differential D, and I want to introduce a sequence of operators, R0, which is going to be identity, so R1, R2, and so on, such that, so that's the condition of delta being homotopically trivial. So delta is homotopically trivialized, better to say, if we have chosen this R0, R1, and so on, such that D plus Z delta, Z is just a formal variable is equal to, and then I'm writing here, okay, so I'll denote by R the sum Ri Z to the power I, and I'm writing so R inverse dr. So that's what in some other branches of mathematics people call Hoysch to DRAM degeneration data. So, okay, good. And the point is the following. So now what I'm claiming is that if I have BV algebra with this extra piece of data, then I have in a natural way and in canonical natural way on the homology of this BV algebra the structure of hypercommutative algebra. So somehow there is a quasi-iso, well, so theorem if you want. Theorem by many people. So I think that the first who proved it was it was done in a paper of Drummond, Cole, and Valette, and so then people refer to this also as conjectured by Kontsevich. So theorem claims that, well, I'm trying to say it in this way. So let me think for a second. That if you have, okay, so if you have high com in the sense that you want just to abstractly consider these operations, modular relations, relation like that, as a structure. So if you know the language of operands, you can actually think that I'm just talking about this operand, that this is quasi-isomorphic, and actually so there is an explicitly constructed quasi-isomorphism with the following data. So what I have in BV algebra is this, so commutative associative product. So I also have my operator delta, right? And I also have this data of Cauchy-Durand degeneration data. So homotopy trivialization. So this is the mod natural relations that I want. So somehow these two algebraic structures on a pure algebraic level are just equivalent. So it doesn't matter what you're talking about. Whenever you get a hypercommunative algebra, you can always find maybe some bigger BV algebra with a non-trivial differential such that this would be induced on each cohomology and vice versa. When you start with a BV algebra and you get homotopy resolution for your BV operator, then you always get this high-com algebra. Okay, so that's an instance of these relations that I have in algebraic 2D gravitation theory. So, and then before I would explain you, for instance, I mean this extension that I have for operators of any order, I want to explain you a bit more of philosophical viewpoints. So now due to Arnold. So like 25 years ago, so when I was at high school, so me and by the way, so Vladimir Dotsenko as well, so we went to a public lecture of Arnold for high school students. And one of the most important thoughts that we learned there was the following. So Arnold explained that all nice things in mathematics are coming in, and then he used the word trinities. I even checked because I was a bit surprised. I was used triples, triads, or whatsoever, but I called before giving this talk to several former Arnold students to check that it should be called trinities, and they all, yes, replied that Arnold insisted on calling them trinities, and he gave many examples. So I wrote, I mean, some of them from that lecture. So examples of trinities are like R, C, and H. So also like when you are talking about singularities, so this E6, E7, E8. So then Arnold discussed Stiefel-Rietving classes, Chern classes, and Pontryagin classes. So he also discussed homology, K-theory, and so elliptic homology. And actually, so there is a whole list. I mean, I just give a few examples to give a sense of what he meant by trinities. And he had actually explanations why, in some sense, they all form the sort of what he called trinities by the same rules. And you see the result that Jörg just erased. Let's test it whether it's a good one in the sense of Arnold, whether it's a part of trinity. Right? And can I ask you to leave this one? Yes, yeah, please. Thank you. Yes. Yeah, good. Because yeah, I'll just needed to correct with this B. Okay, good. So I want to extend. So actually, this is not the full list of Arnold. So he also talked about Z2 coverings, so S1 bundles and SU2 bundles. And there are more of this kind of trinities that he argues are all interrelated to each other. And so that was important for him, that they all should be interrelated. And now I want to extend the list of trinities. So I want to put here the following. So I want to put here just trees, usual trees. So trees. So here I put, looks the same, but it's quite different. It's plane trees. Plane trees. And so what should be here? Here we should have what I call bamboos with tendrils. What is bamboo? Bamboo is a tree like that, and tendrils, you see, you can also have some like that. So this is bamboos with tendrils. Good. So then I want to discuss a bit further. So namely, what I would put here is, for instance, commutative associative algebras. So here just associative algebras. And here some just commuting operators. And actually, so I can extend it further. And so as you see, so I want to put all this algebraic two-dimensional gravitation theory that I just discussed. Well, I discussed only a small bit of it, but I want to put it here. So this is like HiCom centered HiCom, so commutative, let us say, to the gravitation theory. So the question is, what should be here? What should be there? Right? If it's a nice thing, then according to Arnold, by the same rules, he moved, for instance, from the middle column here to the left to the right. Well, roughly by the same, because it's all philosophical and metamathematical. You should also be able to move here and here, right? So let's try. Then we'll know whether it's a good theory. And then I can discuss, because it's still we have to talk about topological recursion. So whether we have something to offer in this picture on the side of whether topological recursion is actually a nice piece of science in the sense of Arnold, whether there are any trinities, right? So we have to test what we are doing, I mean, according to the best standards, I think. So let me discuss. Good. So first I want to go to, let me keep this result, and I want to try to generalize, but the point is the following. So of course, my first idea is, so let's try to check what we can get if we move from commutative associative algebras to associative algebras. So what would be if we, instead of hypercommutative algebras here, these totally symmetric operations, we would try to get totally non-symmetric operations, right? So that would be moved to the, if I look like this, to the right in Arnold trinities. So surprisingly, there exist nice definitions in the literature, and so this is a kind of work we did a few years ago with Vladimir Dotsenko and Bruno Vallet. So I want to explain you some bit of it, namely, it's come down, and then I'll explain. So namely, what already existed in the literature is if you have an associative algebra, which is totally non-commutative. So, okay, so this is going to be non-commutative BV. So, so people knew what is the order of operator in a general associative algebra, non-commutative. For some reasons, I mean, this is due to I think to Borjesson and Martin Markov. So these kind of definitions. So they, by the way, when I'm talking about the order of operator here, I mean the order of operator in the sense of Cajul, in the sense of Cajul braces. But I can be more specific. But in any case, so what I want to say here is that so imagine that you have okay, so product which is associative, but totally non-symmetric, so non-commutative. So what does it mean if I have this kind of structure on my algebra? What does it mean that I have operator? I'll still call it delta. which is of some order, right? And the definition is like that. We say that this operator is of order less or equal to b if for any vectors a1, a, b plus 1, I have the following identity. So this is the definition that we didn't have to invent. It existed for their own algebraic reasons, which are not important for us at the moment. So identity would be like that. First, I have to take a product of these guys. By the way, the order is important. So I really put here a1 and up to a b plus 1 should be exactly in this order because it's no longer commutative. It's associative, but no longer commutative. And then I apply my operator delta. So minus, I'm writing. So then I do the following. I take the product of all of them except for the last one, AB, apply delta, and then take the product with the last one. So then I took also minus, and then I do A1, and here is, so delta applied to the product of A2, AB plus 1. And then the last term is plus, so plus what should be there? It should be like that. It should be, so the triple product, here I put my operator delta, here A1, AB plus 1, and here all the rest of them, A2, AB, right? And this should be equal to 0. So this is the definition of operators of fixed order, of order less or equal to B in purely associative algebras, non-commutative. Good. So the question is the following. Let me keep this. So this I can, so in some sense, you see, I'm starting to try to find the right column for all the guys that I have here. As I said, so the test for any result is whether or not, so now let me do like that, whether or not I get something, well, some correspondence in these Arnold trinities, right? So I already know, so this I don't need, but in any case, so I can put here NC. And then I already know what should be NCBV, right? NCBV should be, as you can guess, just associative algebra plus delta such that delta square equal to 0, order less or equal to 2, right? So the question is, to which structure this would be quasi-isomorphic? So what is the structure that I would see on the homology of an algebra like that? What structure I would see if I introduce homotopy resolution exactly in the same sense as before, right? So question. So whether okay, so does, let me put the question like that. Does so BV slash NCBV, I'm sorry, slash delta makes any sense? Makes any sense? So the answer is yes. Yes, and I can describe it explicitly. So it would be non-commutative, hypercommutative algebra. So you see, I'm fighting commutativity quite successfully. Namely, I would have operations also of arity 2, 3, 4, 5, not non-symmetric in their inputs. Non-symmetric in their inputs of degrees, of homological degrees as they were before, 0, 2, 4, and so on. And the relation. Okay, so now I'm correcting the relation. So the relation is going to be like that. You see, it's now kind of non-commutative, right? It's non-commutative, so I have to draw pictures very carefully. And of course, I can't have 3 arbitrary indices in the non-commutative world. I just can have indices that are, so for any, I would say I minus 1, I, and I plus 1. And then I'm writing here the sum but the sum would look like that. So again, I mean, the analog, non-commutative analog of the WDV relation in this case is going to be like that. I'm saying that on the left, I want I minus 1 and I to be on the top. So first apply operation to these guys. So I would have like this. So this is I minus 1, this is I. And then I would apply here some operation and then the rest, right? Of course, I mean, the inputs are always ordered from left to right. It's non-commutative fault at the moment. And so this is I plus 1, of course, the input number of I plus 1. So this sum is equal to the sum where, okay, so I and I plus 1 are on the top. So I first apply my operation to the sequence of inputs starting from I. And only then I apply to the result combined with the rest of the inputs the next operation. So this is what is kind of structure that is that we can call NC. So this gives me the structure that I would call NC hypercom. Or if you want, maybe it's good to call it hyperassociative algebra. I don't know what is the best terminology in this case. So in this sense, the test is passed, right? So it looks like I managed to extend at least this connection in the 2D gravitational theory to the right? To the H column of Arnold trinities. Okay, can I do it to the left? So let's test the result fully, whether it's a nice result or not. No, okay, so then this is something that, okay, I can explain this as well. So this is something that actually was one of the main motivations of famous paper of Losif and Manin. Actually, I asked them, I mean, what kind of things they had in mind when they were writing this paper. And okay, so what Losif had in mind, I'm going to explain to you. And what Manin had in mind, he told me that he thought it was a good step towards definition of motivic fundamental group. But after all, I mean, so this I think was never later realized. At least I haven't seen any definition based on that. But in any case, let me explain. So now it's so other direction. It's other direction like that. So I have to think now. So it's in CBV, and so now it's this real column. In the real column, I would have the following structure. So this bamboos BV, if you want, or I don't know. I used to call it Losif-Manin BV or something like that, but maybe it's not. So it's kind of in the category. It happens in the category of twisted algebras, right? So that's, in fact, if you want some algebraic background on that. So LMBV looks like that. So this is the real part. So this is, we go to the left. It's the following. So I have, well, something that replaces commutative associative algebra, namely some sequence of operators with form variables t, so such that they all commute. Phi I commutes with phi j of degree 0 on some vector space. And then I'm saying that I have some operator delta on the same vector space. Delta squared is usually equal to 0. And then the order of operator here is defined like that. So of order less or equal to 2. But then I just mean that, so delta definition is of order less or equal to b. If delta, so commutation with phi, and then many times phi, so how many times? B plus 1. Of B or B plus 1. So I have to think for a second. Boom, 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 boom. Yeah. I think B plus 1 is equal to 0. No, B. Let be B. I think B is correct. If delta just commutes, that I think is no B plus 1. Sorry. Yes. No, but if it just commutes, it's a kind of Leibniz rule. So then it's order 1. So I'm checking not order 0, but order 1 indeed. Good. What I want to say, Let's test what happens here. What happens here. So the point is the following, that whether I get also something reasonable here if I take homotopy quotient. So homotopy quotient mod delta. The answer is yes. In the same way, so using the quasi-isomorphisms, as I said, of particular categories, in this case of some twisted algebras, what I get here is called what people normally, so it's what I call here is equations of flat connection. So basically what I get is the following. So let me try to write this. I get where is it written? 2, 3, 4. Yes, here. Good. What I get is the following. So I'm saying that I get equation of flat connection. So basically I say that I have some matrix theta maybe. So that depends on T1. So some operator that depends on my variables. So I maybe from 1 to n, T1, Tn. So it's a matrix, it's an operator acting on my vector space, satisfying. So operator that satisfies so d theta, which d theta is equal to 0. Right, so d theta is the matrix of one forms of a flat connection. Good. So the point is the following. So this is kind of now you can ask me so whether why I'm sure that these three instances indeed would form me here the right contributions to Arnold trinity, right? The answer is the following. So the only test we have is main Arnold's principle, namely, if we add any other natural result to this set, then we should get back again full correspondence along all three cases, right? So that's basically how he explained how the trinity should work. So I want to add, for instance, this result, to check, right? So the result with B. So what is going to happen if I, in the classical case, change the order of operator? Because 2 is justified from various examples in string theory, but why should we necessarily do from algebraic point of view? It's not clear. So let me explain what would happen. So what would happen is the following. So let me take another color for arbitrary B. What would happen is the following. You see, I said that in the case of well, in both cases. By the way, so in this case, I can also maybe I'll get back to that later on. But in case, so I have my definition of usual high comm. And what is usual high comm? Usual high comm is that I have some operator. I have arities starting from 2. So it's arity. So an arity can be 2, 3, 4, 5, 6, and so on. And I have operators some degree. And degree can be, okay, so 0, okay, so they're only even 2, 4, 6, 8, and so on. And then the point is the following. So I have some generator here. I have some generator here of arity 3 and degree 2, generator here, 4, 4, 5, 6, so 6, 8, and so on, right? So these are my generators of high comm. And let us now do the following. I just take a new algebraic structure, a very big one. Namely, I reiterate each operation of arity 2, but in each degree. And that's a new independent operation. So I want to have also operation here, 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 here. And actually, I do the same for each arity and each degree, starting from 0. So I'm sorry that I'm not writing this more detailed way, but the point is that it's very easy to comment it on this diagram, but it's quite complicated to write the full answer. Well, not complicated, but at least, it would distract us. So the point is the following, that, so what happens if I have arbitrary order less or equal to B? So I have to look at all these operations, and I want to impose the usual WDV relations, now not for operations themselves, but for the series of operations. So basically, when I'm writing, so before I was writing, so relations, before I was writing that I have something like this is equal to, okay, sum over this to something like this. And now I mean that when I'm drawing this, I want to take here the sum of all operations of arity3 in all degrees in this place. And here, okay, so this is the sum of all operations of arity4 in all degrees at this place, right? But otherwise, I would just want to keep the WDV relations. So this is kind of extended WDV. Okay, so 3 is 6. Yeah, okay, good. So very good. So then I say that I get this very, very big structure and I look at its quotients. Namely, I take only part of the generators. So I know that if I would just get these generators, so one of each arity in these degrees, then I get usual high common. So this is the case of B equals 2. If I want to get the case of B equals 1, I need to take only these generators with the relations that are quotients of these relations. So this is B equals 1. If I want B equals 3, then I take this line. So I always get straight line through this plane, and it returns with the generators that I have to take for the corresponding homotopy quotient for operator of any order. So then I would have this is for B equals 4, and so on. So you see, it's a kind of answer that keeps us in the realm of rescaled in what concerns the degrees, still hypercommutative algebras. The question is whether this result fits, can be appended to this algebraic 2D gravitational theory, whether it would survive attempts to transport it to non-commutative case and lossy mining case. The answer is yes. The answer is yes, and even the answer is exactly the same. So I have to take, for instance, in non-commutative situation, exactly the same operations. I want to let them have arbitrary degrees as on this diagram. I want to let the series where I take the sums of all degrees satisfy exactly the same relations, and then I pick exactly the same lines of generators. So it's just literally the same. I do not change anything in terms of what happens with this result when I transport it to non-commutative case. So what would happen if I would transport it to this case? No, this case also, I mean, the point is that you can, this theta, you can expand it, of course. You can say that theta is in degrees in t. So you can say here that theta is equal to theta 1 plus theta 2 plus so on. And so this is or like Taylor series in t. And you can pictorially think that this is like a piece of bamboo with one tendril, this is piece of bamboo with 2 tendrils, and so on. And then the point is the following: instead of arity, you have this degree with respect to t's. Oh, sorry, I tried to put it back. But otherwise, so instead of arity, you would have these degrees in t here, but otherwise the result would be exactly the same. So it's perfectly transportable. I have more results of this type. As I said, so it's just a small piece of what we call algebraic 2D gravitational theory. And all this is equally well transported to non-commutative side and to this, well, I call it lossy mining side. So, okay, I have, I think, 10 minutes more. And there are 2 more things that I want to say. One thing is to speculate. So I think it's important a bit to speculate about where it can go. Namely, whether topological recursion belongs to the, how I should say, nice results in the sense of Arnold trinities. And the answer is, of course, I don't know. But what I know, let me explain. What I know is the following. I know that, of course, here it's what I started with. It's our usual good old topological recursion. Here, I don't know. It's really, I don't know, and I have no idea what it should be. But if there's any non-commutative version of topological recursion, not in this direction of non-commutative geometry that the workshop is devoted to, but some other, of course. So then it should be here. And here the point is the following, that in fact, many years ago, Daniel Ivansky has shown to me that when we are thinking about these equations and so on, it can be connected to a kind of topological recursion. Or at least, I mean, the point is the following, it was not clear what to do with it at that moment, because this big picture of 2D gravitational theories, I mean, I didn't know it at that moment, and I also couldn't give any good response to what Danny did. But so here is, you can, at least I can put a name of whom you can ask about what can be here, right? That's the best what we have in any case. So okay, good. And the other thing is the following. So of course, another thing is that I want to discuss is the following. That again, what is the test whether we get good algebraic structures or not, right? So another test is the following: whether it's related, whether we can extend also. There is another thing, I mean, to which these kind of structures are related. And you know that on this in this middle column, it's all related to M0, 1 plus n bar, to these spaces. So these are the dilemma for compactifications of the modular space of curves on genus 0, of the modular spaces of genus 0 curves, right? So we know that this is a kind of thing that controls like genus 0 3 level, but I told you that I'm only talking about 3 level Gromov-Witten theory and so on, right? So here, as I said, I mean, I called it Lossif money not for nothing, but it's just because it's all intrinsically related to the works that Lossif did like 20 years ago in topological quantum mechanics, Lossif and his students. And so what they have written together with Manin about the so-called Lossif-Manin spaces. So Lossif-Manin spaces. That's just a bit different compactification of the points on CP1. It's a different compactification and it has quite different properties, and it's related to many other remarkable things, like, I don't know, these Matroid Chow rings and so on. So the question is whether we have something to put here, right? So whether, yeah.
So on this side, is it related to real curves or not at all?
Very good question, thank you. Very good question, because I was thinking, because honestly, when we understood that we got this triad, and we thought whether that triad is a trinity. And if yes, how to put it, like what is C, what is R, and what is H? So it was not so clear, but okay, so somehow what we get here is so intrinsically complex that I don't touch it, so that's what I have. And the point is the following. So one of the things that in these early papers on this stuff, Lossif was constantly writing, he was relating these algebraic structures coming from Lossif-Manin spaces to Morse theory, but with kind of complexified time. But somehow this Morse theory with complexified time has intrinsic real structure in any case. And another thing to which it is also closely related is to the structures that emerge in symplectic field theory, where you also have a kind of, I mean, intrinsic reality somehow. So yes, so in some sense, yes, it's I mean, we in any case talking about something that is complex, but this complex has in the background something very strong, has some strong reality. Let us put it like that. So the question is what to put here. And I know the answer. I have 5 minutes to explain the answer. And why this answer is in some sense quaternionic, I don't know. So, but the answer is very explicit, namely, so if you think about this kind of algebraic structure, and you think about these operations, for instance, about dimensions, but also there are much more structure than that, and you think whether it's related to the homology, cohomology, and some further structures on some sequence of spaces. The answer is yes. And these spaces are the so-called, so this is what we discovered with Volodya Dotsenko and Bruno Valette. So these spaces are the so-called brick manifolds studied by Escobar. So for those of you who like toric geometry, these spaces are the toric varieties of Ladé realizations of ascahedra. So ascahedra, these are special polytopes, they have different integral realizations, and the one that we need is due to Lodate. So I can explain, I mean, various things about it, but let me just first explain what are the spaces. And in some sense, so what I want to say is that stratification, homology, constructions, and so on, and many other geometric properties of these spaces, they're really in some non-commutative way repeating the properties that we know about M0 and bar, about the Dirichlet-Mumford modular spaces. Okay, so what are the NC, I put in quotes, NC M0 1 plus N bar, right? So this is the following. We have to consider the space of configurations of vector spaces. Namely, I'm writing it like that. So I'm start V11, V22. So the meaning of indices is not important at the moment. So VNN. And I want all the space to be of dimension 1. So then I'm saying that here I have V12, V23, Vn minus 1, n. And this should be of dimension 2. And so on. At the top, I have V1 n minus 1 and V2n. This should be of dimension n minus 1. And that is, and I want this, so this is a kind of queer variety. I want to consider the configurations of vector spaces that are embedded in each other according to this diagram. And with an extra requirement. So they all are subspaces. They all are subspaces of, so this is equal to, in some basis of some fixed vector space of dimension n minus 1. So this is also the same. And the guys that are on the sides, they are like that. So this one is E1. So this one is E1, E2, and so on. So I just add one extra basis vector here, and here I remove one extra basis vector each time. So this one is En. So this one is En minus 1 En, and so on. So this kind of things, now I consider just the full, the space that parameterizes, the algebraic variety that parameterizes the configurations like that, configurations of vector space like this. So this is a kind of quiver Grassmannian for some very specific quiver. As I said, it's a very nice toric variety, and they all together form very nice sequence of what I call non-commutative modular spaces that have many properties that you know about usual modular spaces. Please. E2. Yes. No. I said the indices doesn't matter. It's just convenient to write with two indices to remember which is subset of which. But this one is exactly the same, so they're equal to each other. So they're just the full space where you consider the subspaces. So kind of, I mean, this part, I mean, the boundary of this is fixed, right? It's a fixed thing. Sorry? En is in fact En minus 1. Thank you. Good. So, okay, I have maybe 2 minutes, well, or maybe no minutes at all, just to say that, okay, so first of all, everything you know about usual modular space of curves, what you know, stratification, you know, the kind of, I mean, inductive properties that strata are products of smaller modular spaces, psi classes and their properties, like topological recursion relation and so on. So whatever, I mean, it's hard for me to imagine, you know, for instance, the papers where people compute the real versions, the homology of the real versions of modular spaces. You can also apply it here, replacing complex vector spaces by real vector spaces and so on. It's all fits very nicely in what you could add here, continuing the story about Arnold trinities on that side. So this is the right analog of right non-commutative analog in the sense of Arnold trinities of usual moduli space of curves. Okay, so now the question that I don't know the answer, but I would say that at least, I mean, like a few years ago, I even wouldn't know how to approach this question. But now, thanks to, I don't know, these papers of Kantsevich-Soberman, of ABCD paper of ABC authors, and yeah, maybe so some work in progress that, for instance, Gaitan has. So I think that there are approaches also to have a nice definition of some non-commutative topological recursion. But that's, as I said, so it's more like what I'm explaining in this direction is only what could be a grand proposal, but no results that I know. But so let me stop here.
Thank you. So we can take questions either from online participants or from people in the room.
So this non-commutative M0 n+1 bar structure, it looks a bit related to maybe doubly nested Hilbert scheme of C2. Do you have any idea whether it is?
No, I have no idea, and I don't think it is related.
Okay, thanks.
So yes.
Can I just ask you to say a little bit more maybe about the last comment that you made about the non-commutative version of TR or something like that?
I made in my life one stupid thing. You see, when I mention some works in progress by other people, I normally try to check with people whether they don't mind. For instance, I asked Danny whether he wouldn't mind that I would mention this thing that he did many years ago. I mean, when he was trying to connect loss of money and stuff too. But I didn't check with the people who have some results on this. I didn't ask for their permission to mention their results, but basically what I mean is the following, that so if you think, for instance, about the Kantsevich-Soberman viewpoint on topological recursion, you can try to formalize it algebraically and see what you get, right? And basically you know that on algebraic level, when I'm talking about the middle thing here, I'm in the realm of operats, right? And step here is the step to the structure is called twisted associative algebras. The step here is the step to the structures called non-symmetric operats. So that's a kind of hint one might have to actually find the right definitions of what should be the right version of non-commutative topological recursion in this sense. Moreover, I have some hopes for that. Because, as I said, so here the point is the following. So when I'm talking about this 2D gravitational theory, we have a lot of beautiful geometry hidden here. For instance, this space is very rich, but we don't know how to connect this space to any enumerative problems. We don't have some source of non-commutative Gromfinian theories, and that what could replace it if there are natural examples in this pink circle. Right, and one more remark here is also that what was my remark? Yes. So somehow, I mean, the only idea I have, I mean, continuing, because Arnold writes a lot of speculations about how to produce trinities, right? And one of the things he is writing is, when he's talking about trinities that are incomplete or he doesn't know how to complete. So he's talking that, okay, so what I can derive from what Arnold is writing, that what we should look for here should be maybe some enumeration of maps of hyperkähler varieties or something like that, because so they should so hyperkähler structure should play some role in producing the instances of that. But I don't know further anything, so that's.
Okay, I think we don't have time anymore for official question time, but you can still ask Sergey. He's here till Wednesday. So thank you again.